Hi everybody, this is Mrs. Mancuso, Little Chemistry Review. Today we are going to talk about polarity. So let's say we have two atoms. We have hydrogen and we have bromine. We can look at the reference table and we can check out their valence electrons. So we go over here and we see hydrogen has 1 valence electron and bromine has 7 valence electrons, okay? So 1, 2, 3, 4, 5, 6, 7. Now if they come together and they share, it's gonna look like this. And now bromine has all 8, 1, 2, 3, 4, 5, 6, 7, 8. And hydrogen has 2 in its valence. So they're both very stable, very complete like this. But what happens is there is more of a pull from bromine than there is from hydrogen. And that's because bromine is more electronegative. That means it's able to attract electrons to it more. So they're going to be pulled more towards the bromine side, making this side a little bit negative and this side a little bit positive. And if we look up the electronegativity difference, so we're going to look up hydrogen's electronegativity, and it's a 2.2. And we look up bromine's electronegativity, and it's 3.0. So the difference between 2.2 and 3.0 is 0.8. So the electronegativity difference is greater, or if it's greater or equal to 0.5, then it's going to be polar. That means there is a significant pull of electrons. So in reality, it's actually going to look more like this. If this is my H and this is my Br, the electrons are going to be closer to the Br than they are to the hydrogen. So that's what we mean by polarity. There is a pull on it. When there's a pull, you get a little difference in charge, and those charges make a polar molecule. First of all, they make it asymmetrical, so polar molecules are asymmetrical, but it also makes it have these slight charges, which means that it's gonna like water, because water also has slight charges. Water is another polar molecule. So when you draw out water, here's oxygen, and oxygen has 1, 2, 3, 4, 5, 6 valence electrons, and then there would be a hydrogen here and a hydrogen here, and there's the sharing of electrons. Now the way that I'm drawing it here, I'm showing that the electrons are pulled more towards oxygen, so oxygen is more negative and hydrogen is more positive. So this bond right here is polar. And again, I can look up the electronegativity. So H we already said was 2.2. Oxygen is 3.4. So that means the difference between them is 1.2. So that means it is definitely a polar bond. When you look at the molecule is also asymmetrical, and it has an uneven distribution of charge. So when you look at polarity, you can look at the bond, or you can look at the molecule. This molecule is asymmetrical and has an uneven distribution of charge. So it is definitely a polar bond and a polar molecule. We know like dissolves like, so something like HBr is gonna like water because their charges will be attracted to each other. Things that are ionic have absolute charges, positives and negatives, so they are definitely going to like each other as well. And now let's just do a Br with a Br. So if I have two atoms that are the same, this one had 7, 1, 2, 3, 4, 5, 6, 7, and this one has 7, 1, 2, 3, 4, 5, 6, 7. So if they share these, they are going to have a non-polar bond. I don't have to look up electronegativity. I know the electronegativity difference is definitely going to be 0 because they're both bromine. So this is definitely a non-polar bond. I like to call that nicey nice. There's no pulling. They are definitely sharing equally. The molecule is also non-polar because it is symmetrical and it has an even distribution of charge. When you have a molecule that's larger, like CH4, that 4 right away lets you know it's going to be symmetrical. You can picture a C with 4 H's around it. That is a symmetrical molecule, so that means it's going to have an even distribution of charge as well. All right, let's think about how this affects attractions between molecules. We started talking about it a little bit with polarity. So if something is polar, like water, there is definitely going to be pulls. There's going to be attractions between other molecules. So this is going to have stronger intermolecular forces of attraction. This, I didn't draw any charges. If there's no charges, then there's no attraction to other things. So this is going to have very weak attractions. All right? Thanks for joining me.